Welcome to the channel. I'm Carlos Ortega, and I'm excited to explore the amazing worlds of physics and chemistry with you.
When we stand on a beach and watch a swell roll in, or feel a gust of wind cross a field, our brains jump to a very logical conclusion. We are watching physical matter travel from one location to another. But that intuition is often wrong. Think about a crowd doing the wave at a stadium. You see a clear shape moving around the arena, but if you track an individual person, they aren't moving horizontally. They just stand up and sit back down in the same seat. The same physics apply in nature. If you drop a rubber duck into a pond and a ripple passes by, the duck simply bobs up and down. The water itself isn't carrying the duck forward toward the shore. What is actually traveling in both cases is a wave. A wave is a disturbance moving through matter or space that transfers energy from point A to point B, while the physical matter stays right where it started. Understanding how the universe transmits power and information requires a closer look at the mechanics of that traveling energy. Energy travels through the cosmos, across different environments, from the dense rock of the Earth's crust to the empty void of space. To track it, physicists classify these disturbances by their physical dimensions. This diagram shows the three primary categories. On the left, we have one-dimensional waves, moving along a single axis, like the ripples traveling down a performer's ribbon. In the middle are two-dimensional waves, spreading across a flat surface, like the rings on a pond. And on the right are three-dimensional, or spherical waves, radiating outward in all directions. This is how seismic energy from an earthquake moves through the Earth's crust. We also categorize waves by how the disturbance moves relative to the direction of travel. In transverse waves, shown here on the left, the disturbance is perpendicular. As the energy travels horizontally forward, the rope snaps vertically up and down. Beside it is a longitudinal wave. Here, the disturbance runs parallel to the direction of travel. The coils of the spring compress and expand back and forth as the energy pulses forward. Most of the waves we interact with daily, like the sound radiating from the strum, are mechanical waves. They require a physical medium, whether that's solid, liquid, or gas, to propagate. In a true vacuum, they stop. The major exception is the electromagnetic wave, like the light traveling from the sun to the Earth. These waves generate their own oscillating electrical and magnetic fields, allowing them to carry energy through the vacuum of space. Regardless of the medium, all of these waves share a single, universal mathematical structure. Because this energy is often invisible, we rely on a standardized set of parameters to measure and predict its behavior. This graph maps the profile of a transverse wave. The first parameter is amplitude, the maximum distance a point travels from its flat resting position. The taller the amplitude, the more energy the wave carries. Next is wavelength. This is the physical distance between two identical, consecutive points on the wave, from one peak directly to the next. As the wave moves, we measure its frequency. This is a count of how many complete wave cycles pass a specific checkpoint every single second, measured in hertz. From frequency, we find the period, which is its mathematical reciprocal. The period tells us the exact amount of time it takes to complete a single oscillation. By multiplying a wave's frequency by its physical wavelength, we calculate its speed of propagation. With those numbers, we can map the precise profile of any traveling energy in the cosmos. Those mathematical profiles are perfectly ordered on paper, but we usually only perceive this energy when it crashes into a boundary and interacts with a new environment. When a wave strikes an impenetrable boundary, it bounces back into its original medium. This is reflection, the physics responsible for the echo of your voice in a cave or the image you see in a mirror. This visualization shows the mechanics of refraction. When a wave enters a medium with a different density, its speed shifts. Because the wavefronts enter at an angle, one side slows down before the other, causing the entire direction of travel to bend. You can observe refraction in a simple glass of water. If you drop a pencil in, it looks broken at the surface because the light waves reflecting off the pencil slow down and bend as they move from the water into the air. When traveling energy encounters an obstacle or passes through a gap roughly the same size as its wavelength, it changes direction, bending around the corner and spreading into the space behind it. This is diffraction. We apply these specific wave behaviors to engineering. Reflection allows for ultrasound medical imaging, while radio waves diffracting through hallways ensure Wi-Fi signals reach around corners in our homes. The physical matter making up our world is largely static, but the light we see, the sounds we hear, and the signals we use for connection form an overlapping web of traveling energy, perfectly executing the great illusion of movement.